talk about the second chapter of physics, which is actually on your thermal processes. So previously in the energy chapter itself, you remember that there was one process where energy is transferred, right? It is by heating. So this is actually referring to that method itself. We are transferring heat because there is a transfer heat, right? Because there's a higher temperature and a lower temperature itself. So this only stops when you reach the same temperature. So when you reach the same temperature itself, basically it means that you are in thermal equilibrium where there is no net transfer. Because remember, you only transfer heat when you have a hot object and a cold object. If both of them are equally hot or equally cold, there's no heat transfer at all. Therefore, you don't have that. Okay? So for your heat question itself, the very first and most important thing is you need to first identify if your object is hot or cold. Because if your object is hot, right, for example, you need to remember that because I'm hotter than the surroundings, I will lose heat. And if my colder object is here, because I'm colder than the surroundings, I will actually gain heat. So if these two are put actually side by side itself, the amount of heat that you lose is equal to the amount of heat that you gain. Just remember, energy cannot be created nor destroyed. Same thing for heat. You cannot just create or destroy heat out of nowhere. You must gain or lose heat to something else or from something else itself until everyone is the same temperature. Okay? So firstly, let's talk about your first method, because for your heat transfer itself, there's actually three different types. Number one is conduction. So conduction itself basically is very important because it involves vibrations from one molecule to another itself, and mainly it is through your solids where there is direct contact. Because the thing is, particles are actually considered to be quite far away from each other, right? So by actually direct touch, so you ask yourself, how do you know if you have conduction? Number one, my object must be touching the second object itself. So for example, usually when something is hot, how do we test it out? We usually will poke it, right? So same thing, we touch it to see if we know whether it's hot or cold itself. Okay, now this below here, this part here is asking you to describe how conduction takes place. Okay, and if you still recall from your lower secondary itself, is that non-metals are poor conductors of heat, while your metals itself are generally good conductors of heat, right? So why is that so? What's the reason why? Number one, particles gain heat and vibrate more vigorously, right? And then what happens? Number one, because particles when they bump into their neighbors, they transfer energy. Okay, so same thing. I also have particles here, and I also have free mobile electrons. So the thing is, both of them will gain heat and move more vigorously. Okay, and what's so special about your free mobile electrons is that they are faster moving itself, and they can travel directly to the colder part, collide and transfer your heat. So because of this, you can just imagine, because I have both methods, I have both the particle vibration and I also have the free mobile electrons. Because I have additional free mobile electrons, I can actually transfer heat faster than non-metals, which only have particle vibration. So if they ask you to compare and explain why, it is just this part. Because metals conduct heat by both particle vibration and the movement of free electrons. Whereas for non-metals, I only conduct heat by vibration of particles. Hence, metals are better conductors of heat than non-metals. Okay, so this one is mostly for the why question. The one on top is mostly for the how question. How does, for example, my plastic cup, how does it conduct heat? The plastic particles near the hot water or in contact with the hot water will gain heat and vibrate more vigorously. They will collide with neighboring particles, transferring heat or transferring energy to them, so that when another person, when they actually touch the hot plastic cup itself, they will actually just feel warm. Or you can also talk about how water heat is actually being spread throughout itself. Okay, but for metals itself, if you were to touch a metal cup that is blazing hot, because particles and free mobile electrons are transferring heat through the collisions of particles, when you actually touch it, what happens is that those faster and more energetic particles and free mobile electrons will actually come into contact and with your finger, and they will transfer heat to you very fast. So as a result, you will burn your hand. So you need to be careful. A lot of this is really based on context. Like I said, thermal chapters is quite straightforward because it involves quite a bit of memorizing. As long as you understand how it works, it is easy. However, the questions are very application based. It really depends on the context of the question. So if you're not familiar, you haven't memorized, you never really put in much effort to go and study this chapter, you're gonna have a very hard time, because this chapter really involves you understanding how each and every one of these processes work and how you apply them properly to the question. So I would say that this is one of the more difficult chapters itself. So you need to brace yourself and put in more effort to actually tackle this topic itself. Okay? So apart from just the what and the why, and what else affects conduction? When we talk about affecting conduction itself, we're talking about the speed, the rate of heat transfer. So normally when you see that we say that, oh, you're a good conductor of heat, what does that mean? I gain heat fast, I also lose heat fast. So it really depends on the context of the question itself. If you are poor, you have to use this. So if you want to use poor itself, you will either use a plastic or a non-metal. And then if you want a good, you want to have a metal. So when do we want to have a good? When do we want to have a poor? That's the key thing you need to identify. So in the work example below, you have the side view and the top view over here, and it's used to hold hot cups, hot drinks. Okay, important, huh? So firstly, my object is hot. If I'm hot, I lose heat. Okay, so if you want to hold the cup without being scalded itself, I must lose heat slowly. So ask yourself, which part of the design allows you to be a poor conductor of heat? Because if you want to lose heat slowly itself, I must, number one, I must be a poor conductor of heat. So what makes this a poor conductor of heat? Okay, so number one, the design traps a layer of air between the cupboard. Trapped air is a poor conductor of heat. Now, if you don't know why it is a poor conductor of heat, it is actually because remember, particles of any objects, they conduct heat through the vibration of particles. Now, remember your solid, liquid, gases. Solids are very closely packed together, but liquids and gases itself, they are considered to be further apart. So if you're further apart, it's much more difficult for your particles to vibrate and collide with another neighbor. If you're very far apart, at most you just vibrate about fixed position, you may not even hit any neighboring particles itself, especially for gas. Okay, so your trapped air, which is a poor conductor of heat, reduces the rate of heat transfer by conduction. Now remember, when we talk about heat transfer itself, from where to where, just like from what energy store to what energy store, heat transfer is from the hotter object. So from the hot drink to the cooler hand of the user. Thus, the user can safely hold the cup without being scalded. Now, if you don't know what scalded means, it just means being burnt by hot water. Okay, if you play Pokemon, Scald is also a very useful ability that causes 30% chance of burning. Okay, so this is how it works. And for now, if you have two different cups, you have one which is in this format, corrugated copper cup, and one you have a ceramic cup itself. Now, if you were to leave them at room temperature, which one will contain temperature at a higher temperature? So number one, first thing you need to identify is I have hot drinks. And after some time, which one is cool, which one is hot, right? That's what you want to find out. So this one is I lose heat slower. So now this question is basically asking you to compare my corrugated cardboard cup versus my ceramic cup. Now both of them are non-metals, right? So now you need to justify which do you think is the poorer conductor of heat, because if I'm a poorer conductor of heat, I will lose heat slower. Okay, so the answer is the corrugated cardboard cup. Okay, it will contain the coffee at a higher temperature. Okay, so firstly, trapped air is a poorer conductor of heat because number one, it is a gas. Okay, compared to ceramic, which is just a pure solid, trapped air, because the particles are much further away, they are actually considered to be a much poorer example. And if you were to notice, I keep mentioning the word trapped, because later on, the next video itself, you'll notice that when we talk about moving air, that will be a different process altogether, okay? So trapped air is a poorer conductor of heat than ceramic, so the rate of heat loss from the hot drink, rate of heat loss by conduction. Okay, from the hot drink to the cooler surroundings is reduced or slower because you're comparing, right? So only when you're comparing itself, then we use comparison words like faster, slower, poorer, better. Then we use all these. Okay, so ultimately this is the reason why the corrugated cardboard cup is better than a ceramic cup itself. So that's why usually if you go to like clinics, polyclinics or hospitals itself, usually the cardboard cup or even Starbucks, okay, or those kind of coffee bean, usually the cup that they give you to hold hot drinks usually will have a certain design such that when any user holds the cup, they don't actually burn their hands and drop the cup. Okay, so next time if you go to a coffee shop or those kind of fancy cafe itself, go and double check for those takeaway hot drink cups.